good morning, or good evening. My name is Dougal Ballantyne. In today's webinar, we're going to be doing a deep dive into maximizing EC2 and EBS performance. So what we're going to cover in the webinar today is an overview of Amazon Elastic Block Service. We're going to dive into the volumes and snapshots, how we maximize the performance of volumes and how that relates to EC2 and the choices you make, encryption, and then we'll spend some time doing Q&A at the end of the session as well. We have moderators in the webinar today, so if you have a question, so as I was saying, a lot of our customers understand all of the characteristics of a hard drive or an SSD and what those mean for an architecture when they put it together. And so, you can build a system, and if you get the right number of hard drives, you can build a complex RAID configuration, and you can pull all that together, and that really is what drives, well-performing applications. The important thing to understand here is EBS is not a hard drive. EBS is a service, and because it's a service, it comes with different characteristics than a typical hard drive may present. So what is EBS? So EBS is network block storage. It's attached to your EC2 instance, but it's independent from EC2. It's designed for 5 nines of availability. So because it's a service, we actually have availability goals within the EBS service. So how long a volume is available for I/O, and also durability as well. You can attach an EBS volume to the same within the same availability zone as your EC2 instance. And we also provide point-in-time snapshots to Amazon S3. So EBS leverages the durability of S3, which has 11 nines of durability, to make snapshots or copies of your data that you can then use to restore EBS volumes if there was a problem, or to create EBS volumes in other availability zones or even in other regions. So a little bit more about EBS. As I said, I want to really iterate, it's a service. So it's not a hard drive attached to your machine. It's not just a large collection of drives. It's a service. One of the things that enables us to do is make improvements to the service. And so if you've learned a little bit about EBS before, some of the things we'll cover today are going to show you how EBS has evolved and the new capabilities, and that's because it's a service. Completely independent of EC2. You can attach and detach from EC2, but it's not running on EC2. It's part of a separate service. We have our availability goals, which I touched, and just a little indication of just how big EBS is today. There's over 1.5 million volumes created per day, and that's a lot of volumes created. So before I get too far into the presentation or into the webinar today, I think it's important that we set a few definitions. And some of these may be familiar to people already, but these definitions are going to come up multiple times, and so defining them early will help us make sure we're on the same page. So IOPS, or input-output operations per second, is typically presented as a number, and it's one of the attributes of a volume. Throughput, read and write rate to storage in megabytes a second, and that's how much data we can move backwards and forwards between a volume. Latency, typically measured in milliseconds, and that's the amount of time it takes for a request to be sent and the response to be received. Capacity, typically measured in gigabytes or gigabytes, and that is the size of the volume or the amount of data that you want to store. And then the block size, the size of the IOs which are being sent backwards and forwards between your application and the block device, and then also in turn being sent between the EC2 instance and the EBS service. So let's dive a little bit deeper into EBS and the different volume types. So today there's actually 3 volume types for EBS. We have General Purpose SSD, which is the default for AWS. We have provisioned IOPS, which has got a higher level of performance consistency, typically directed at databases and things like that. And then we have the original EBS, which is called Magnetic or EBS Standard. When performance matters, use SSD-backed volumes. So you're going to see throughout the webinar, we have little highlights that we really want to be takeaways for you. So if you're thinking about things that you really want to remember from the webinar, they're going to be highlighted like this. And so again, if performance matters within your architecture, you should be using one of the SSD-backed volume types. So a little bit of data around what those volume types present. All of this data applies to both general purpose volumes and provisioned IOPS. So an IOP, or an IO, is measured up to 256 kilobytes. So what that means is if you send down a 1 megabyte IO, so that would be the block size of your application, it will be chopped up into 4 IOPS measured at 256 kilobytes a second. Now that is different from where it was last year, where it used to be 16 kilobytes. So this actually means you can do substantially higher throughput on your volumes than you could in the past without using up your IOPS. So you can actually provision less IOPS for higher throughput on them. They're all designed for single-digit millisecond latency. Now it's important to understand EBS is designed for single-digit millisecond latency. To achieve single-digit millisecond latency, you need to make sure your application is also architected correctly as well. And all EBS volumes are designed for 5 nines of availability. So let's dive a little deeper into the EBS General Purpose volumes. So it's the default volume type for EBS now. When we say default, we present things on the console. So if you're launching an instance or you're launching an AMI, and it doesn't use GP2 or General Purpose SSD as the default volume, we will alert you on the console and let you change that going forward. They also operate something called a burst bucket, and we'll spend some time in the next slides explaining that in more detail. But every volume can burst up to 3,000 IOPS, and larger volumes, if they have a higher baseline performance, will actually go a lot higher than that. You can go up to 10,000 IOPS based on 3 IOPS per gigabyte, and they have a 99% performance consistency, or they're designed for 99% performance consistency, and a throughput of 160 megabytes a second. To explain the burst bucket a little bit more, we're going to use a graph. So the volume size, which is the x-axis, and then the IOPS, which is the y-axis, shows us as the volume size increases, the baseline IOPS, which is the green line, will continue to grow. Once we cross the 1 terabyte or 1,000 gigabyte size of volume, you'll notice that we actually have a higher baseline than the burst bucket. So the burst bucket is in yellow. That's the ability to burst up to 3,000. Above that, the baseline performance exceeds the burst, and so you'll always be able to achieve the baseline performance. So understanding the burst bucket a little bit more. So every single volume that's created in GP2 starts out with an IO credit bucket of 5.4 million IOPS. And you can spend those IOPS up to 3,000 IOPS per second. Now, if your baseline performance exceeds 3,000, your bucket is never going to empty. That's because it's always accumulating at the baseline performance. So if you have a bucket which has got 100 IOPS, if you have a bucket that has 100 IOPS, 100 mega, excuse me for a second. If you have a volume which has 100 gigabytes, it's always going to be accumulating at 30 IOPS a second. What we do see in practice, though, is customers rarely actually empty their IO buckets. We have single-digit percentage of customers over the life of GP2 since it launched have actually exceeded their IO credit bucket. And that's because as the volume sizes get larger, the time it takes to empty your bucket is substantial. So on this graph, we're showing volume size on the x-axis and time on the y-axis. And as you can see, I think I have it highlighted here, a 500 gigabyte volume takes 60 minutes before you empty the IO bucket. And so that means you would need to do 3,000 IOPS constantly, no change, for 60 minutes before the volume would actually start to run out of IOPS in the credit bucket. Volumes over 1 terabyte, as you can see, will never exhaust their bucket because they have a higher baseline performance than the IO bucket. A couple of examples of what this does now for EBS volumes. Microsoft Windows tends to be quite chatty on the boot volume when it's launching. And so if we take a 30 gigabyte boot volume, the initial volume will always get a credit of 5.4 million, and it could burst for up to 30 minutes non-stop at 3,000 IOPS. And it's always accumulating 90 IOPS per second because it's a 30 gigabyte volume. What that does is it significantly improves the boot time of those systems. So if we take a look at the Magnetic boot time, it was 4 minutes and 30 seconds. If we look at the GP2 boot time, it was 3 minutes and 31. But what's even more interesting is the access time. When is the system ready to be used? When is Windows fully booted and available? And that drops significantly, a 40% reduction in boot time. So if you haven't done this already and you have some older AMIs in your environment, you should make sure that you're using GP2 volumes to boot those instances. Another one which is rather interesting is the impact that GP2 has on database volumes. So previously we didn't have GP2, we only had provisioned IOPS and standard. And so customers would choose provisioned IOPS for all database workloads. However, when we start to take a look at what GP2 can do, a customer is actually able to achieve significantly higher IOPS, all the way bursting up to 6,000 IOPS for a quarter of the price, or actually more than that. And so you could launch a 1 terabyte GP2 volume and get 3,000 IOPS for $102, but that would be less than the 4,000 you previously had. But you could also launch 2 GP2 volumes at 500 gigabyte, do a RAID 0 stripe, and get a baseline of 3,000 and a burst to 6,000 at the same price. So you can do some very interesting things with GP2 for database volumes. Some general guidelines for sizing GP2 volumes, how you should approach that. In general, just provision the size of volume you need for most applications. So if you need 500 gigabytes of storage for an application, provision 500. For database applications, you want to calculate the number of IOPS you think you'll need in steady state. And then you would take the steady state IOPS divided by 3, and that will give you the number of gigabytes you should provision. You should note, though, that for I/O bursts, things like loading the database or scanning the tables, they're going to be handled by the burst buckets. So those are not going to be included in your steady state. So you should be able to use significantly smaller volumes when you remove those. Moving into the second SSD volume type we have, which is EBS provisioned IOPS. They're best for I/O intensive databases that require the highest consistency. So when we say the highest consistency, what we're referring to there is the performance consistency of the volume. So if you have a tier 1 database service that cannot tolerate a stall for a couple of seconds when you're doing a select in the database, provisioned IOPS is the type of volume you'd want to run that database on. It's got a significantly higher throughput than GP2 volumes, so they're able to drive 320 megabytes a second. And you can provision twice as many IOPS, so 20,000 IOPS per volume. And they have a different gigabyte to IOP ratio of 30 versus 3. So when you really need to drive a lot of IOPS from a small volume or a lot of throughput from a number of volumes, provisioned IOPS is going to enable you to do that. And again, it's designed for 3 nines of performance consistency, enabling you to really build tier 1 solutions on top of PIOPS. Not forgetting EBS Magnetic, or standard EBS when it was launched, is still a really good use case for things like cold workloads or data that you don't access very frequently, but you do want to have it sitting on a file system rather than maybe archived in S3 or Glacier. You can achieve about 100 IOPS steady state, and the throughput is variable based on the workload. It's typically in the tens of megabytes a second. And the latency is also variable. This is really, it's designed for cold, random access or rare access rather than the throughput type consistency you'd get with the SSD volumes. So a little bit of a cheat sheet, and I should at this point also share that we will of course be making sure all the materials are available after the webinar, so you'll be able to look at these cheat sheets offline. This really just sort of covers everything we've covered in the introduction or the overview of EBS here. There's a couple of interesting items to call out, and that's, for example, we show the max number of IOPS per node. So when you're running on our larger instances, you can actually RAID volumes together and achieve even more IOPS than a single volume can present, or more throughput than a single volume can present. And we give you a summary of the pricing as well. So why did we make GP2 SSD the default? Well, it provides a high baseline level of performance for all workloads. So by using GP2, customers with multiple workloads don't need to choose different volumes. They can use the same volume type and get good performance. It's got a good burst to higher level of IOPS, so workloads that are spiky are naturally going to be a good fit. We've also changed it to a single capacity-based pricing, so you only need to know how many gigabytes you're going to use in the volume to work out the price. There's no charge for IOPS or throughput. And it provides a really attractive price, gigabyte price, IOPS density. It's a lot in there. So we feel like it's the sweet spot for a large amount of workloads on top of EBS, and that's why we've made it the default. One takeaway, if you're not doing it now from there, is please make sure you're using GP2 SSD volumes for boot. The speed up is significant and it makes the management much easier. There's no IOPS charge if you've got a large workload on top of your boot volume. How do you migrate to GP2 volumes? So if you've got data that's sitting today on a magnetic volume or standard, or you've got data that's sitting on PIOPS, you can just change the volume type during launch for some of that. So if you're launching new systems from a snapshot, then you can do that. You can use EBS snapshots to migrate data. So if you have data today on a magnetic EBS and you want to move it over to GP2, you can just snapshot that data and then use that snapshot to create a new volume, which is GP2. You might actually be able to resize your file system afterwards. So if you've been working on provisioned IOPS and you'd over-provision the number of IOPS because you wanted a baseline and the burst is now going to accommodate that, you might be able to do a resize when you create the new file system. And use the sizing guide we provided earlier to work out what size of volumes you want to migrate to. So let's talk a little bit about EBS snapshots and why you'd want to use EBS snapshots. So an EBS snapshot is more durable than an EBS volume. And that is because when we take an EBS snapshot, we copy the data from EBS and we store it in Amazon S3. Now we don't store it in your bucket. You can't go to Amazon S3 and see the data. What we do is we use Amazon S3 as the location and we store it as a snapshot format for EBS. But what that means is we get the durability of S3 now for storing that data. And so if there was something to happen with a volume, either a volume was corrupted or maybe you had some data loss, you're going to be able to go back and find the snapshot and use that snapshot to create a new volume. They're differential or space efficient, meaning the first snapshot is a complete copy of the EBS volume. And then after that, the second snapshot, the third snapshot, is only a copy of what has changed since the last snapshot. So if you have a 100 gigabyte volume, the first snapshot is going to be 100 gigabytes. If you change or write 10 gigabytes of new data onto that, the second snapshot is going to be 10 gigabytes. And then the same goes on. So the rate of change will determine how big your snapshots are. They're independent of availability zones. Because they're stored in S3, they're a regional concept. So you can take an EBS snapshot and use it to create another volume with the same data in another availability zone, or you could actually copy it over to another region or even share it with another account. When you're working with snapshots, I think one of the things that's really important is to start tagging them. So with tags, you can actually start to build up metadata that makes it easier to search for snapshots or find snapshots within the EBS service. So tags like the type of snapshot, daily, monthly, weekly, the version, so if you're doing version control, you can keep a version in there. Things like instance ID are automatically populated. The application is not, so you might want to ensure that you're keeping data for the HRDB or you're keeping data for prod or dev or test. And these tags will help you later to find snapshots to create new volumes from. So that was the overview of EBS. What we're going to do now is start to dive a little bit deeper into the performance and some of the choices you should be making if you're designing for performance with EC2 and EBS. So before I go too far into this, I want to start with a little bit of theory. So Little's law is the foundation for almost all performance tuning theory. It's a mathematical theory proven by John Little in 1961. These pieces of data, so the average queue length, the arrival rate, and the wait time, are all data which we expose today in EBS, and you can observe both inside your EC2 instance and also on the CloudWatch metrics. And using this law, you can actually determine whether you're getting the most performance out of your environment and what's to change. So performance optimization is typically measured in three ways or in three areas. The amount of IOPS that you want or the amount of IOPS that you're achieving, the latency so the amount of time it's taking for those IOPS to occur, and then the throughput, exactly how much data is being moved backwards and forward. And throughput is actually a calculation of IOPS multiplied by IO size, so what is the block size of data you're transferring. Those three areas are where we're going to focus our optimization and how to get more performance. There's four key areas where we can make choices or make decisions when we're maximizing the performance. So the first one is the EC2 instance, and we'll spend some time talking about the characteristics of EC2. The I/O, so understanding what I/O you're sending from your application and making sure it's optimized appropriately. The network link, because as we mentioned, EBS is network attached block storage, so therefore the link between EC2 and EBS is important. And then the EBS volume itself, the size of the volume or the number of IOPS you've configured. We have 6 different areas where we can focus or make choices to design for performance. The EC2 instance, whether it's an optimized EC2 instance, the workload itself, understanding that, the queue depth, so that is the arrival rate in Little's Law. We can also use RAID to increase more performance, and then pre-warming we'll touch, which is the last thing we have to cover on performance. So let's start with the EC2 instance. So when you're choosing an EC2 instance, we typically present them as EC2 instance families. So we have compute optimized, memory optimized, general purpose. Now customers, when they're choosing their instance, they're typically looking for a number of cores or an amount of RAM or a certain ratio between cores and RAM and the space that provides. One of the other characteristics of an EC2 instance is the amount of network bandwidth that it has connected to EBS. And so when you're selecting that, you need to make sure you have the right size of instance for the amount of data that you want to be doing. So if you launch a T2 micro and then you want to attach a 20,000 IOP 10 terabyte EBS volume to it, it's not likely to be able to drive enough I/O to that volume because it's a very small instance against a very large volume. So it's important to right size your instance, not only for the workload that's going to be running on it, but also for the amount of EBS that you want to have it accessing. So when you're choosing EC2 instances, you also want to be looking for instances which are EBS optimized. An EBS optimized instance is an instance which gives an amount of bandwidth dedicated to EBS. So when we think about that network link, it's going to actually allocate an amount of network traffic so that you can ensure that EBS traffic is passing over a different network path than instance traffic, which might be requests to your database or web pages that are being requested from a web server. EBS instances are available across all of the latest generation instances, so the M3s, the M4, C3, C4, R3. And in our latest generations, so things like the C4 and the M4, they're EBS optimized by default, so you don't even need to choose the flag anymore. On our largest instances, things like the 8 extra large and now our 10 extra large instances, they actually support all the way up to 10 gigabits of EBS optimized traffic. The maximum number of IOPS each instance can do is actually 48,000 IOPS, and you'll see that as we go through in our cheat sheets, and that's on our largest instances, the 8 extra large, for example. So the takeaway here, if you want consistent EBS performance, use EBS optimized instances. If you've launched instances today which are not EBS optimized, you can change that. It's very easy to do. If you go into EC2, you can actually do a stop instance and then change the EBS optimization flag on and then press start instance, and it will come right back up just like a reboot with an EBS optimized instance versus without. And that will give you a more consistent EBS performance if you're going to be using a lot of EBS traffic. So understanding the workload. If you don't understand your workload, it's going to be very hard to determine what throughput, what actual performance characteristics you expect to achieve from the application. And so when we're thinking about workload, the areas where we dive in are around the I/O size. And when I say I/O size, I'm referring to the I/O size the application makes. So an application could be doing very, very small reads and writes, so something like 4 kilobytes, or it could be doing very large ones, like a Hadoop cluster, for example, does very large reads and writes. And those reads and writes, the size of them is going to have an impact on the number of IOPS that are consumed on your volume. The I/O pattern, sequential or random, and so EBS will actually attempt to do something called I/O merging, and I/O merging is the ability for EBS to take I/O requests which are contiguous or sequential and put them together into one request. So if you send two 64 kilobyte requests and they happen to be beside each other from an EBS perspective, they'll actually be merged together at best effort to 128 kilobytes, reducing the number of IOPS it takes to generate on your traffic. The I/O type is important to understand, so whether it's a read or a write. You can actually do interestingly on EBS, reads and writes do not have any different throughput characteristics. You can read and write at the same number of IOPS, which is quite different from a normal hard drive environment. And then I/O concurrency, the amount of I/O that's happening. And we're going to spend a little bit more time in the next few slides diving into what I/O concurrency means. But I/O concurrency is essentially the queue depth that is being presented on your block device. And one of the big changes with EBS SSD volumes is that IOs are now measured up to 256 kilobytes a second. And I already mentioned that we deliver the same performance for read and write. So I want to explain a little bit of concept around EBS IOPS and throughput. So when you create volumes, or when you're using EBS, the volumes have two characteristics. They have their throughput and they have their IOPS. Now, the IOPS and throughput are related together, but they're also independent. And so if we take an example of a volume, for example, an 8,000 IOPS PIOPS volume, you can drive 8,008 kilobyte IOPS, you can drive 8,016 kilobyte IOPS, but you can't drive 16,000 IOPS. And the reason for that, obviously, is because it's IOPS limited. Even though it's underneath the 320 megabytes a second throughput, you can't drive more than 8,000 IOPS. However, you can't drive 8,064 kilobyte IOPS because that's above the 320 megabytes a second. And so it's important to understand, when I was talking about the last slide's workload, that you know what the size of IOPS your application is driving and whether it's exceeding the throughput limits or whether it's exceeding the IOPS limits on the volume. The block size is going to determine that. So what size of blocks that your application is reading and writing is going to be a big component in that. So queue depth. So queue depth is the amount of IOs which are waiting to go into the block device. And queue depth is an important aspect because with a network attached block storage, a higher queue depth or a lower queue depth will impact our latency, and we'll see in the graphs as we go through. So when we're monitoring those aspects, so when we're looking at queue depth, we're looking at the latency. All of this data is actually going to be presented in the CloudWatch metrics. And so what I mentioned at the beginning around Little's Law and the ability to understand what's happening with your volumes, you can actually take a look at the amount of IOPS read and write, the average latency, and the actual throughput of the volumes to see whether those volumes are achieving what you expected or whether you have bottlenecks in your architecture. So I/O latency, a little bit deeper in here. It's the elapsed time between I/O submission and its completion time. Your performance may be driven by IOPS or by latency, and there is a very strong interdependency between IOPS, queue depth, and latency. So when we take a look at latency, this is what it looks like in one way to present this. Now, the reason I have this in here is to show you that when you're collecting data on something like latency, it can be rather overwhelming. So all of the red dots in here are read operations, and then all of the blue dots are write operations. And they're over a time period of 120 seconds, all of the different latencies for all of the different IOs that occurred. And it's quite hard from this graph to see whether we're making progress as we make changes. So what I want to introduce here is something called the boxplot. And the boxplot enables us to have a much more interesting view of how I/O within our volume is being performed. And so the center of the box has a median line, and so that's the median of the I/O. Then we have a 75 percentile, or P75, a 25 percentile, which is the P25, and then the top legs on the boxes are our 0 and 100 percentile. And so what we're going to do here is show you how you can measure, but then also improve the latency of your application. So I want to start with a baseline. So this baseline is some measurements of latency for an application we were testing on an M2 4 extra large using magnetic volumes. And as you can see, the box is rather large and the range is rather large as well, so logarithmic scale on the y-axis. And so it's definitely up into the very high milliseconds for the P100, and the P75 is actually pretty close to 10 milliseconds, and we're seeing some requests in P25. So only under 25% of the requests are actually under a millisecond. If we move that to GP2 volumes, so this is what the second box plot shows now, We're still on an M2 4 extra large, but now we're using GP2. You can see that our median has come down substantially closer to 1 millisecond now for the I/O latency. And the whole box plot is now sitting significantly lower on the scale, so we're seeing much more of our I/O in single-digit millisecond latency now. However, we still see quite a large variability, so we're still seeing some I/O which is in the 10 millisecond range, and the graph is going all the way down into the half millisecond at the bottom. Let's make one more change to the I/O here. So if I move from an M4 4 extra large to an R3 2 extra large, which is one of our latest generation memory optimized instances, you can see the box plot has become substantially smaller. The median is on the bottom of the box plot. Our TP100, which is the very top line, is still single-digit millisecond latency, and there's very little variability in our I/O latency. So it's a flat line if you're looking at it on a line graph. All we changed there was the volume type and the instance type. But what's really interesting is, if you take a look at the cost, we've also reduced the cost. So by using the latest generation EC2 instance, the R3 2 extra large, we get the same memory footprint, the same number of vCPUs, a newer CPU, we get the benefit of enhanced networking, and we drop the price from 98 cents an hour to 70 cents an hour. So if you're looking at driving latency or reducing latency in your workloads, this is one way to walk through and to understand how you can do that. I want to talk a little bit around how queue-depth impacts your latency. Now, queue-depth is I/O concurrency, or the amount of I/O that's pending to go into the block device. What this graph shows here, the x-axis is queue-depth and the y-axis is latency TP90, so the 90th percentile of latency in milliseconds, is that as we increase the queue-depth from a queue-depth of 1 on the left through to 32 on the right, our latency goes from being 0.075 milliseconds all the way up to 35 milliseconds. And so when I said that EBS is designed for single-digit millisecond latency, it's important to understand that your application is also in charge of how much latency is going to be introduced based on the queue depth. And so if I start to add in here the amount of IOPS which are achieved with queue depth, because the two have a correlation, you can see that I need to have a reasonable queue depth before I'm able to achieve all of the IOPS I'd like. This is a 4,000 IOPS volume, so it's a volume capable of doing 4,000 IOPS. And if you look at the queue depth of 1, which I've highlighted here, we're only achieving 1,865 IOPS. So even though the volume is provisioned for 4,000, we don't have enough I/O concurrency to the volume to actually achieve all 4,000. It's only when we start to move into a slightly better queue depth, a queue depth of around 2, that we actually see that it's possible for us to achieve 4,000 IOPS. We're still single-digit millisecond latency, but we need to have a higher queue depth, so more concurrency on the volume before we achieve it. We can also see that if we increase our queue depth too far, so a queue depth of 35, we're actually getting under 4,000, and we're now getting 35 millisecond latency on our I/O. So it's important to understand if queue depth is causing a problem. Now, queue depth can come as a problem when you have, for example, a lot of I/O concurrency on a volume that doesn't have a lot of IOPS. So if you have 100 IOP volume or 1,000 IOP volume and you're sending a lot of I/O to it with many, many threads or a large database on it, you'll see your queue depth is going to go up and then your latency will go up as well, which means that you're trying to drive too many IOPS through the volume. And just to show you that write latency has the same graph and the same curve, read and write is the same on EBS. And so again, with write, at 1 queue depth, it's substantially lower, but if we move the queue depth closer towards 4, you see that we're able to achieve 4,152 IOPS on the volume. So the takeaways here, use SSD volumes with the latest generation EC2 instances, and the optimal queue depth to achieve lower latency and the highest IOPS is typically between 4 and 8, or around 1 queue depth per 500 IOPS. At the end of the day, you're going to have to observe this using the CloudWatch metrics to get a perfect number if that's what you're trying to achieve, but typically starting anywhere between 4 and 8 will give a good number. And EBS optimized instances will provide consistent latency experience because the network path between the EC2 instance and EBS is going to be dedicated to EBS traffic. So what if we need to drive more than a volume can deliver? So we launched larger and faster volumes, and with a larger and faster volume, you can now do all the way up to 16 terabytes or all the way up to 20,000 IOPS. But what if you need more than that? And so when you do, you're going to need to start to think about things like RAID. And so we don't think about RAID for redundancy within EBS. EBS is already replicated within the availability zone and it has a very high durability and availability. So RAID is there to increase the volume size and therefore increase the volume throughput or volume IOPS. You don't want to mix volume types, so it's very important that if you're going to be doing a volume that you make sure that the volumes are well sized and well balanced. You don't want to have a GP2 volume attached to a magnetic or a PIOPS volume for RAID. And we typically see customers doing RAID 0 or LVM stripes because that is the way to increase the throughput or performance. So what is the maximum performance you can drive from an EC2 instance? So I just wanted to share some of the numbers we've done before and customers are able to achieve. You can drive, as you can see highlighted, with 8 threads. So that's ensuring that we have enough concurrency going towards the volume. 48,000 IOPS from an instance, or all the way up to 823 megabytes a second. And that's with rated volumes, so you do need to put the volumes together. So when you're doing RAID, the big takeaway is use a large stripe size, so 128 kilobyte or 256 kilobyte. That's because it's going to map into the I/O size that's seen by EBS and reduce the number of IOPS. If you have a small size, you're going to generate more IOPS than is necessary on your RAID volume. Now, I do want to spend a little bit of time talking about pre-warming. So pre-warming is something that happens or is something that's necessary when you're doing benchmarking or you're validating the performance of a volume. There's a first access penalty on EBS. So the first time a block is touched, it's a little bit slower than any other time in the future. And so if you're doing performance benchmarking, one of the things you can do is you can write some data to the volume that will eliminate the first touch penalty. And then you'll be able to use the volume and the expected performance going forward. We typically don't see customers having to do this a lot. It's only for benchmarking. And you should always check our documentation, the link is here, to understand what the current best practice is, because I said earlier, EBS is a service, and so we're always evolving the service. So it's best to check in the documentation to make sure that pre-warming is necessary or if there's any changes to the procedure. If you are going to be pre-warming, use a really big block size. So you want to write something like a 1 megabyte or a 2 megabyte I/O to the block device so that it's used up quickly. And some final tips around volume performance on the Linux space. Try and use an ext4 or XFS file system. The volumes are getting larger and larger, all the way up to 16 terabytes now. And these file systems support something called lazy init or lazy inode creation, enabling you to create the volume substantially quicker and not be bound to the volume create time. Especially if you're doing things in user data or Chef or Puppet, it can take a long time to lay down a file system on 10 terabytes of data. And alignment can matter. In fact, it does matter. You should check that the tools you're using in your operating system understand 4K sector alignment. EBS presents itself as 4K, and you should make sure the tools, so in some older versions of Linux, they didn't understand 4K, things like fdisk, etc. So another cheat sheet for folks to go over, really just highlighting what we think are the sort of throughputs, the amount of throughput per instance per volume you should be able to achieve with different applications. And like we see on the right-hand side there, all of the systems should be able to achieve 48,000 IOPS, and the different workloads will generate different amounts of traffic on a 500 megabytes EBS versus a 1 gigabyte EBS optimized instance. So just to recap a little bit, if we get the 4 key components balanced, we'll be able to drive bandwidth and throughput IOPS all the way through the system in a balanced configuration. So you can do a lot of I/O to EC2 from EC2 to EBS if we get everything balanced. So we choose the right size of EC2 instance. We use an EC2 optimized instance, so we control the size of the bandwidth between EC2 and EBS. And then we right size our EBS volumes, the right number of IOPS or the right size for the throughput. And we're able to drive a lot of I/O. And just to recap, the tools you have for tuning or the things you can choose when you're trying to architect for performance. The EC2 instance, so the amount of network transfer speed it's going to have available to it. So obviously a very small instance can't drive a very large volume. EBS-optimized, so making sure that your EBS traffic has got a dedicated network path to the EBS service. Understanding your workloads, so making sure you understand whether it's read or write heavy or whether the block sizes are appropriate for what you've set up. The queue depth, so making sure the I/O concurrency, if you want to make sure that you're driving the lowest latency or the most throughput, make sure you understand the queue depth. You're able to use RAID if you want to get even more performance out of the volumes. And you may have to, for benchmarking, make sure you get rid of the first touch penalty before you start making numbers. So that was the performance section. So now we're going to quickly go into the encryption section. And encryption's another great feature of the EBS service, which is easy to turn on. So why would you want to encrypt? Like why are people encrypting their data volumes? So it helps you protect against accidental unauthorized access to a physical volume. The keys are going to ensure the data on there is encrypted. It can help with your internal or external compliance efforts. So your CISO may want all of your sensitive data encrypted, or you may have, for example, PCI compliance or HIPAA compliance, and third-party auditors would like to see evidence that you're able to encrypt your data. The reason that we've added EBS encryption in is it's easy to use and reduces the operating cost. And so unlike some of the open source or third-party solutions, EBS encryption today offers checkbox encryption, so you can just tick a box and say encrypt my volume. And we also provide automated secure key management. So part of EBS encryption is AWS Key Management Service, or KMS. And so if you really just need encryption turned on, then you don't need to worry about where the key's stored, where the key's managed. But if you want to manage the encryption keys, you want to manage what service has access to them, when they're used, be able to see things like CloudTrail logs, be able to revoke keys, then you can use AWS KMS to manage those for the EBS service. If you want to create an encrypted volume, it's really as simple as choosing the tick box on the console or in the API saying encrypted. And you can provide a master key, which is one of the KMS keys, if you want to use a customer managed key versus the EBS service key. And how it integrates is just to give a little bit more insight in the background of what happens. So KMS uses a hierarchy of keys and does something called envelope encryption. So what that means is KMS is actually handing out a data key to the EBS service, and then the EBS service is using that key to then generate volume keys, so that we're not going back to KMS every single time the EBS volume needs to be accessed. It's only going back when the data key needs to be accessed. It gives a much better scale and enables us to manage a smaller number of master keys rather than millions and millions of data keys for all the volumes we have. And so a little summary of the webinar we've gone through, and hopefully we'll have some time for questions. And so the first thing is make sure you select the right volume for your workload. Okay, so we have 3 volume types today, and they all have different characteristics. We think the default volume for most customers is going to be EBS General Purpose, or GP2. But make sure you're selecting the right volume, the right volume size, and provisioning the right number of IOPS if you're using provisioned IOPS. Make sure you choose the right EC2 instance for your workload. So if you want to be doing a lot of heavy I/O, make sure the instance is capable of driving that amount of I/O at EBS. Take snapshots often, use snapshots a lot in your environment. Snapshots will make it possible for you to move your data to other regions if you want to. It'll make it easy for you to build a dev test environment from existing data sets. And it also means that if you had something happen to your data, you can easily go back to a snapshot and use that. And definitely use encryption if you need it. It's a checkbox, you can turn it on and then start to use customer managed keys as well. It's very simple and very easy to implement in your environment. So let's move over to doing some Q&A. So